Hello everyone, we are Group 2, and today we will present our topic on Chinese font style transfer based on conditional GAN structure. Here is our introduction and motivation part. Our motivation of doing this topic is that we want to generate characters or different fonts, so we can reach some purposes like including recreating lost words like ancient Egyptian hieroglyphs or simply creating a new font. Originally, we wanted to change the style of handwritten character. However, due to a lack of Chinese handwriting datasets, and also the few handwriting datasets we found consist of messy handwritings, so we can even recognize the word ourselves. So we decided to go for another route. We decided to focus our topic to style transferring between different Chinese fonts. Actually, there is a fact that creating Chinese font is a difficult and time-consuming task. According to some statistics, if you want to create a set of Chinese fonts that meet the standards like GBK, designers have to create more than 26,000 Chinese characters by hand, which is very likely to take several years to complete. Therefore, we want to develop a way to transfer between different fonts without those time-consuming work by this project. Here are some related work. To be honest, there are few references on the topic of Chinese font style transfer, since there are too many Chinese characters. Also, the features of Chinese characters are way more complicated to be refined compared to the English alphabets. So we only find similar works on English sentence handwriting style transfer, which is still quite different from our topic. Now, we get our data set from image drawn from PIL. We collect the commonly seen Chinese character in the dataset, which will look like this in the picture. And the font is called 霞雾文楷 in the first picture, 轻松手写体 in the second picture, and 王汉中中行书法 in the third picture. The size of our character images are 64 times 64. We split the dataset into two parts. The first 2,000 characters are used as training dataset, and the remaining characters are used as testing dataset. And our baseline is pixel to pixel. Pixel to pixel is a method that learns a mapping from input images to output images. Pixel to pixel is not application specific. It can do a wide range of tasks like synthesizing photo from label maps, constructing objects from edge maps, or colorizing images. Here are some examples of pixel to pixel. As for us, we want to use it in handwriting style transfer. And for the baseline, we choose conditional GAN as our main model design. A GAN consists of two important elements, which is generator and discriminator. Generator is responsible for generating an image, and discriminator is responsible for determining an image is fake or real. Originally, generator takes some noise as an input, and in conditional GAN, we will also take the original font as input. It will generate an image and send it to discriminator. Now, the discriminator will determine it's fake or not. After a round of this, we can calculate the loss of generator and discriminator. As for how, I will discuss it later. With those calculated loss, we can backpropagate it to both generator and discriminator, and they can improve their weights based on the loss. Just like this picture. Now, this is the structure of discriminator. The discriminator is composed of 5 modules. Each of it is composed of convolution layer, batch normalized layer, and ReLU layers. And the last module will compose of convolution and sigmoid layer. It will output a 0 to 1 value to tell us how fake is the image.
The original objective of the GAN can be expressed as this. For the samples from phone 2, we want to let the discriminator to output the result more closer to 1, as well as the samples from phone 1. When we add it with a random noise Z, the generator will output a fake image, and we want to let the discriminator discriminate it with the value more closer to 0. However, the generator is tasked to not only float this discriminator, but also to be near the ground truth. So we choose to use the L1 distance to encourage it has less blurring on low complexity patterns. And the L1 loss can be described as the following. And therefore, the total loss function of the generator can be described as this. We want to find the generator that minimizes this total loss function. The parameter lambda determines the proportion of the loss. In our test, it is given the value 100. And here are the experimental methods. We implement the generator with encoder-decoder structure and also the UNet structure. We want to compare the performance on capturing local features and embedding the font style. The first one is the encoder-decoder structure. Please reference the traingn.py on the GitHub to see our implementation. Our design consists of 6 convolution modules for the encoder, 1 fully connected layer for the noise concatenation, and also 6 convolution transpose for the decoder. The input takes in an 60 by 64 image and also output an 64 by 64 image. The second main approach is to implement the UNet structure. Please also reference the traingn.py on the GitHub. Our design also consists of 6 convolution modules for the downsampling and 1 fully connected layer for the noise concatenation, and also 6 convolution transpose module for the upconvert. The most important part is that we want to connect the previous module and the later module. This connection will ensure that we will preserve the local features and the font posture. Here's our result and analysis. With the same loss function and the parameter lambda, we train both modules over 1,000 epochs. We can observe that UNet has converged quicker than the encoder-decoder structure, and the loss of the UNet is smaller too. However, there are still fluctuations at the layer epoch. Here is some example output when we take the input image. The left-hand side is the input image. The second column is the ground truth, and the third is the output of the encoder-decoder structure generator, and the fourth is from the UNet. You can also see that for the first row, third row, and the fourth row are from the training dataset. The second row and the fifth row are from the testing dataset. Here is our evaluation metric. We normalize the pixel value between 0 and 1 with the threshold 0.5. Then, we evaluate the generator performance by the following 2 ways. The first is the pixel accuracy. It is the proportion of correctly predict pixel to the total pixels. The second is the mean intersection over union. We calculate the ratio of the intersection and the union of its black pixels. It provides a better assessment in case of class imbalance, as it takes into account both false positive and false negatives. And here's our evaluation on the training data set. The columns are evaluated under different epochs. We can observe that UNet has a better performance. However, as the epoch increase, both of the gain and the accuracy reduce. Here are some samples from the training data set. We can observe that for the encoder-decoder structure, during the process of the encode, some of the features might disappear or get blurred. Therefore, the skip connection between the layers of the UNet can confront this problem and keep more details. And here is our evaluation on testing data set. we can observe that the difference on the performance of both encoder-decoder structure and the UNet is little. It is a failing of the overfitting even if the accuracy is high. The value of both modules are close to 90%. However, it's still being worse than the training dataset. Therefore, we can take a look at some samples. Here are some samples from the testing dataset. And for the third row, we can observe that the UNet has captured more feature and posture about the words. However, for the words that are more complicated, the module can only rebuild some of the key components, as well as the others are getting blurry. Here is our limitation of the words and also the further improvement. The first one is our model can only transfer between the selected font, and the question will be how can it generate the arbitrary font. The second limitation is that the result is not good when the inputs are some unseen characters. And how can we confront this problem of overfitting problem on the blurring result? The third is that GN is hard to train and it requires a long time to train. Is there any other better structure or method that can be used to train to do the font transfer? The fourth is that it may generate a wrong but similar character. How can we tune the model to focus on the character components? And here is the practical use of our project. As a previous mentioned problem, how can we get a good result on an unseen character? Since our module requires paired character with different font style. However, the cycle GN may be a desired way to confront this problem, since the dataset between the two font styles are independent. We then can prepare two font style datasets. The dataset is not needed to be 100% same words. If we want to generate lots of words that are not appear in the dataset, then the cycle GN can help us to generate those words that we want to have. And here's our GitHub link, the reference, and the contribution. And this is all our presentation.